question 2 is asking, describe the relationship between, and the A here is the radius of the cation and that of the atom from which it forms, and the radius of an anion and that of the atom which it forms. This is number 2. So this is the difference between atomic radius and ionic radius here. Atomic versus ionic radius. So let me take case A here first. So case A is asking us the radius of a cation and that of the atom from which it's formed. So let's look at some type of cation first. So a cation is going to be probably a metal, right? Because a metal is going to lose its electron to form a cation here. So let me take lithium, for example. So I have Li versus Li positive, right? So what I can do is I can draw the Bohr-Rutherford for both these atoms here. So Li, so for Li here, draw this guy here. In the first shell, I'm going to have 2 electrons. In the second shell, I'm going to have 1, right? And then for Li plus, it's very similar to this. Oh, sorry. In the first shell, I have 2. And then you realize in the second shell, I don't have an electron because I've given away this valence electron away to some type of non-metal or whatnot. So in this case here, that is going to be my atomic radius. So let's compare our radiuses here. And as you can see, Li here has 1 more extra shell than Li plus, which means lithium is going to be bigger. So you can say that the radius between the atom, so this here is the atom, this here is the ion, this here is the ion would be smaller. So so therefore we can say that the cation formed. Remember, Li positive here is the cation. Cation form has smaller radius than atom from which it's formed, which it was formed from. So this here is the answer for question 1. So I'm taking lithium, for example, and then for case B here, we have the anion here. So let's take a look at case B. In case B, we'd have to actually look at a halogen or some type of non-metal here, because those are typically anions. So let's look at fluorine, for example. Fluorine here is F versus this would be F minus for the anion here. So I'm going to draw out my Bohr-Rutherford for F here. Okay, this is a very bad circle. I have the first shell, I have 2. In the second shell, I'm going to have 7, right? 1, 2, 3, 4, 5, 6, 7. And the F minus would simply just be F, but I would gain an electron, right? So it would be satisfied with the full shell. So it's 1, 2. 1, 2, 3, 4, 5, 6, 7, and 8. And now this one is a little bit harder to see, but which one it has a smaller radius, or which one would have a bigger radius? And in this case here, the anion formed. So let me backtrack here. So for cations here, we know that cations here form a smaller radius than this guy here, because I'm basically losing a shell here, right? So this means that the cation here is slightly smaller than the atom which is formed, and we have this here is the anion here. So this one would be F minus, and then what we can do with F minus is we can look at both of these kind of Bohr-Rutherford diagrams here, and we can see that both of these guys are very, very similar, right? We have F minus here, we have F here, which has 2 shells. The first shell here is full, whereas the second shell here would be smaller. And then for or sorry, the second shell would be full, also full as well, or close to full, very, very close to full. It's again seven electrons short. And then for F minus here, we also have two shells, right? Except the difference here is the second one here, the second shell is actually full as well. So in this case here for the anion, and now we're looking at, okay, what about the size of these ions here? So again, these positive anions here, we said that they were smaller in radius, and in this F minus here, these negative ions tend to be bigger than their neutral atoms here. So that's going to be our answer for this problem here, and anions here are going to be bigger than their respective neutral atoms. So cations are smaller, and anions are going to be bigger. If you need help with this concept's really this concept is kind of talking about atomic radius and talking about ionic radius and how in terms of the periodic trends between those two properties there. So if you want more information about that, you can definitely take a look at, I believe I did a video already for OneClass talking about atomic radius and ionic radius, so you can definitely check that out as well. So let's look at this. And this is a typical trend here. So for example, specifically for fluorine, this one, fluorine actually doesn't follow this trend because because it has a full shell here, this tends to be actually smaller than the fluorine neutral atom. So in this case here, the fluorine actually doesn't follow the trend. But for example, if I had O minus versus O1 minus, or sorry, I have neutral oxygen versus 1 minus, then this would follow the trend here. So it really depends on whether or not it satisfies that full shell, because if it does satisfy that full shell here, it tends to be a little bit smaller due to the shielding and the effective nuclear charge of the atom. So in this case here, this specific case, the anion's actually smaller because it has a full shell, but typically in anions here, oxygen and like O minus, 1 minus, for example, are going to be bigger. So I'm going to say typically. So let me rephrase this. That means I didn't do the greatest example with fluorine. I should have picked another non-metal here. That's okay. So let's say typically. Anions have bigger radius, radii, than their neutral counterparts. That's going to be the answer for this problem here. So as you can see here, the A here says the radius of the cation is much smaller than the corresponding neutral atom, which is good. So we said it was smaller radius. And B here, the radius of an anion is much larger than the corresponding neutral atom. So I said it was larger, which is good. However, again, there's actually exceptions to this rule when it comes to having a full octet. And you explore more of that kind of when we're talking about atomic radius and shielding effect and effective nuclear charge, because in a full shell, like what we have here, for F minus, these electrons are actually very much attracted to the positive core in the nucleus. So it's actually going to tend to pull towards the nucleus, making actually the atomic radius smaller. So in this case here, the solution here is correct. But there are exceptions to this trend, specifically yeah. So I'm going to say solution is correct. Again, this is in general. We're talking about a general trend here.